All right, let's do this. Before we jump into electrochemical cells, we need some definitions. We need to define a few terms. So we have four of those terms here. Really only three of these we're ever really going to look at. But we have electric charge. This is the charge on a proton, which is also the charge on an electron, just opposite in sign, which is 1.602 times 10 to the negative 19 coulombs. It's probably not going to come up much after this point. I think there might be one practice problem where we do actually need the charge of an electron, or a question in the homework. But more so than the other things defined here, we are interested in electrical current and electrical potential. So current is the movement of charge, and it is measured in amps or amperes. Usually it's just, you just say amps because it's easier, shorter. And then electrical potential is the force trying to move the charge. So it's the thing that's pushing the electrons as they move through the wire or whatever it is that's happening. So current is the actual movement of the charge. Potential is the thing that is pushing it. It's essentially determines how much energy the charge has as it moves. And then the last one, there's the electrical field, and this is a force acting upon other charges in the vicinity, and we're not going to really worry too much about electrical fields. If you take Physics 2, you are going to worry about electrical fields. It's going to be one of your biggest worries. Electrical and magnetic fields are all over in Physics 2, but this is not Physics 2. This is Chem 2, and so we are not going to worry about it. So let's talk about voltaic cells. So in a spontaneous oxidation-reduction reaction, electrons are transferred and energy is released. So we have a reaction like this one that can occur spontaneously. Take a piece of zinc, dunk it into a solution containing copper 2 sulfate. The copper will spontaneously accept 2 electrons from the zinc and plate out onto the zinc, and the zinc will then, having given up those 2 electrons, go out as a zinc 2 plus ion into solution. That will happen spontaneously. You don't have to do anything to make it happen. All you have to do is make it possible for it to happen. You have to dunk the zinc in there, and then it will start happening. There is energy associated with this reaction taking place. And if you just have the reaction taking place as shown here, most likely what will happen is just that solution will get hot. Because the energy that's released has to go somewhere. And so if it can't be utilized elsewhere, it most often just goes into making heat. Depending on the type of reaction, it might even give off light or something like that, but that, as far as I'm aware, that doesn't ever happen with redox. That's with other types of reactions. So to try and harness this energy, which is what we want to do here, we have a source of energy, we want to harness that energy to do what we want. We can do that by forcing the electrons to not just go directly from one side of the redox reaction to the other. We can force them to travel through some kind of an external device, and as they do that, we can use the power, use the energy of those flowing electrons to do work. And this is a voltaic cell, which is just a fancy word for a battery. Every battery is one kind or another voltaic cell. So by forcing those electrons to not just go directly from the zinc to the copper, but forcing them to travel through a wire first before they can get to the copper, we can utilize the energy of that movement of electrons to get something to happen. So every voltaic cell is going to have a basic setup that looks something like this. Now, your modern day battery does not look anything like this, but that's because all these parts that you see here are kind of all smooshed together. They're all not intermingled. There are definite separations between the parts, but we've taken the simplest way of viewing a voltaic cell and put it here. Oddly enough, there's more parts here than in the lithium battery that's in your pocket right now, in your phone. In terms of the actual number of parts of the battery, the number of sections in the battery. There's actually fewer parts to that lithium battery than there is to this voltaic cell, but it's easier to see what's going on with this kind of a voltaic cell. And so what we have here is we have what we call the anode and the cathode, which are terms you're probably familiar with. You've probably heard those terms before. And if not, don't worry about it. It's not something you have to have heard before. But the anode is the oxidation side of the redox. So this is where oxidation occurs. And it is the negative side of the voltaic cell. So if you go to your cabinet and you pull out a AA battery, you'll see that one end of the battery is marked with a negative sign, the other end of the battery is marked with a plus sign. The negative side of that battery is the anode. That is where oxidation occurs. The other side is the cathode, and that is where reduction occurs. The easiest way I know to remember that is just to remember that the vowels go together and consonants go together. So O and A, oxidation, anode, reduction, R, C, cathode. So vowels go together, consonants go together. That's the easiest way I know to remember that. Oxidation occurs at the anode, reduction occurs at the cathode. So if we think about what's happening in these voltaic cells, we have oxidation occurring over here, which means that we have something giving up electrons. So the zinc gives up 2 electrons to become zinc 2+, and those 2 electrons go whee through the wire to the other side of the voltaic cell. And as they're doing that, you're forcing them to flow through something and using that the power of that movement of electrons. In this case, we just have a little light bulb, but it could be anything. And when they get to the other side, they are given to an atom of copper, which is then pulled in to it's plated out onto that piece of solid copper. So a copper 2+ ion takes those electrons. Now when we think about what's happening here, as soon as one of those electrons moves from this side of the cell to the other, we will have a charge imbalance. Because if all that's happening is we have zinc giving up electrons and turning into zinc 2+, and then those electrons coming over here and forming copper from copper 2+, if there's no way for anything else to happen other than those two processes, the reaction will not continue to go because we'll have an imbalance of charge. All of a sudden, we've lost negative charge over here and gained positive charge, and we've lost positive charge and gained negative charge over here. There's a charge imbalance, and as soon as one of those electrons flows, all the rest of the electrons will be repelled because there's extra negative charge on this side of the cell, and no more electrons will want to come over. So to balance that out, to make sure that things continue to flow, we need what we call a salt bridge, or an electrolyte is another term for this. And what the salt bridge does is it allows other ions to flow back and forth between the two sides without being an electrical conductor, in terms of you can't get electrons to travel from one side to the other. So we can have ions flow to balance out that charge. So as the electrons are moving from the anode to the cathode, carrying negative charge with them, nitrate ions in the salt bridge are also moving to essentially replace that negative charge. And so the charges still end up balancing out. It's just the electrons are still moving, which is the key thing here. We want those electrons to keep moving. So this salt bridge is essentially completing the circuit, if you're familiar with that phrase or that process. If there's not something here completing the circuit where the electrical charges can balance each other out, then the cell just won't move forward. It won't happen. Nothing will happen here. But as long as we have that salt bridge completing the circuit, we are good to go. So this is pretty much what I was just saying there. So we have that salt bridge, U-shaped tube that contains a salt solution to keep the charges balanced. So the cations move towards the cathode and the anions move towards the anode as the cell is discharging, as it is providing power. All right, so in the cell then, electrons leave the anode, flow through the wire to the cathode. As the electrons leave the anode, the cations formed dissolve into the solution in the anode compartment. So we have this movement of multiple different things happening inside of our voltaic cell, with the end result being you have electrons moving from over here, from the anode side to the cathode side. That is the main result that we are worried about, is the movement of those electrons. As the electrons reach the cathode, cations in the cathode solution are attracted to the now negative cathode. So we have some positively charged stuff over here that says, ooh, electrons, I like those. And it comes over and it grabs the electrons off of the cathode. The electrons are taken by that cation and a neutral metal is deposited on the cathode. So that was the basic summary of what's happening here, or these last two slides. The basic summary of what happens when you're discharging a voltaic cell. So then that leads us to the question, why the heck does this happen in the first place? Like, we understand, yeah, the redox reactions, and just chemical reactions happen. We understand, at least to some extent, why chemical reactions happen in the first place. But why do these electrons move through the external circuit and have the energy required to do work? And the answer to this is potential energy. But it's a different kind of potential energy than what we've looked at up to this point. It's easiest, I think, anyway, to think about this in terms of a waterfall. It's a good analogy for what's happening. If you think about a waterfall, water only flows spontaneously in one direction in a waterfall. And the reason it does this is because when the water is at the top of the waterfall, it has a high gravitational potential energy. And so when it's at the top and it's given the opportunity, it will fall to a lower gravitational potential energy. The universe is lazy. Everything's always trying to get to a low energy. Nothing likes to be at high energy states. So the water spontaneously falls from high energy to low energy. And the same thing is true for your voltaic cell, except instead of being high gravitational potential energy, we have high electrical or chemical potential energy on one side versus the other. The electrons in the anode material are not necessarily upset about being there. It's not like they're angry being in that anode material, but they would be at a lower electrochemical potential energy if they were in the cathode material. They would essentially be happier in the cathode material. And so if you give them the opportunity to move from the anode to the cathode, they will do that. And depending on how much happier they would be in the cathode versus the anode, that determines the voltage, which is kind of like the height of the waterfall. If you have a little bitty tiny waterfall, like, you might have a grandmother or an aunt or someone that has little, or maybe even you, I don't know, you have a little, one of those little tiny waterfall things that you just, sit next to your bed, and it pumps the water up like 3 inches up, and it trickles down the little fake rocks, or real rocks maybe. A little tiny little 3-inch waterfall. By the time the water falls those 3 inches from the top of the waterfall down to the bottom, it doesn't have a whole lot of energy. It hasn't moved very quickly, just because it doesn't have time to pick up speed. Whereas if you are at Niagara Falls, it's a much bigger waterfall, much taller waterfall than 3 inches. And so the water, as it's falling down that waterfall, has a lot more energy. It's the same way with voltaic cells. Certain voltaic cells, there will be a lot bigger difference from one side of the cell to the other, and those cells that have a big difference, where it's much more stable for the electrons to be in the cathode material than the anode material, that will have a bigger voltage. the electrons essentially really want to get to that other side. They have a really high speed in a sense, although they're not necessarily actually moving faster. But the change in energy, the change in that potential energy is much greater. So they are giving off a lot more energy when they go from one side of the cell to the other. By the way, is it possible for water to get from the bottom of the waterfall back up to the top? Think about that for a second. Can water go from the bottom of the waterfall to the top of the waterfall? If you are thinking no, you would be incorrect. It absolutely can get back up to the top. You just have to get a bucket and carry it there. The water can absolutely get back up to the top. It just won't spontaneously go back up to the top. But absolutely, you can get water back up to the top of that waterfall, which is exactly the same thing you do with your cell phone every night. When you plug your cell phone into the wall socket, you are giving those electrons a push to go back to where they were in the anode. They wouldn't do that otherwise. That's why you have to plug it up to the wall. You have to have something else that essentially is pushing harder than the electrons wanting to stay in the cathode. So your wall socket is taking buckets of electrons back up to the anode, so that when you wake up in the morning and unplug your phone, now you have all your electrons back over here, ready to drop back down again and provide you with energy. All right, I think we will call it there for today, or for this video anyway. We'll pick up next time talking some more about the electromotive force, also called the cell voltage. So I'll see you in the next video.